In the 1960s, as the Cold War spurred hundreds of rapid advancements in military technology, the world's first operational supersonic bomber, the Convair B-58 Hustler, flew ahead of all others. The Hustler pushed the limits of speed with its 4 turbojet engines, achieving Mach 2 at altitudes of 64,000 feet, with the ability to deliver nuclear payloads with precise accuracy. That is, when flown right. Mastering the Convair Hustler proved to be much harder than it seemed. The model demanded the highest skill and focus from its crew, equipped with complex systems that could be as challenging as they were advanced. Isolated in their separate compartments, communication was often reduced to mere hand signals or rudimentary note passing. The faster it went, the harder it was to control, and even small errors could have dire consequences. Despite the razor-thin margin between triumph and disaster, to the Strategic Air Command crews, just attempting to fly this groundbreaking once-in-a-lifetime aircraft was worth it. The Cold War era's endless quest for supersonic flight birthed the Convair B-58 Hustler. The development began with the Generalized Bomber Study, GEB-1, in the immediate post-war period when the United States invited leading aerospace firms to design a bomber that could surpass the sound barrier while carrying a substantial arsenal. By 1952, after rigorous competitive assessments under the renewed GEBO-2 program, Convair's innovative design emerged victorious against proposals from other top contenders like Boeing, North America, Douglas, Curtiss, and Martin. With official approval secured, Convair propelled the B-58 into its maiden flight in 1956. Equipped with 4 General Electric J79GE5 turbojet engines, each providing a thrust of 10,000 pounds force, which increased to 15,600 pounds force with afterburners engaged. This power enabled the aircraft to achieve a top speed of approximately Mach 2, roughly 1,320 miles per hour at altitude, with a service ceiling of about 64,000 feet. In November of that year, in its public debut, the model took off from Carswell Air Force Base in Texas. The aircraft's 38-minute flight, conducted without the use of the external pod or afterburners, captivated an audience of about 30,000 spectators who before this knew relatively nothing of this new model. The following month, the aircraft would achieve its first supersonic flight, complete with the now very recognizable sonic boom, further demonstrating its advanced design and performance. The B-58 Hustler sought to redefine the capabilities of strategic bombing with its Mach 2 flight potential. The name Hustler was coined spontaneously when E. Stanton Brown, an engineering administrative supervisor, heard of the aircraft's impressive performance and replied, quote, "Sounds like it'll really be a hustler." The B-58 Hustler, designed for rapid, high-altitude nuclear payload delivery, showcased groundbreaking advancements in aerospace technology, particularly in aerodynamics and structural design. The initial challenge was to achieve stability at supersonic speeds. During early wind tunnel tests on the XCF-92A, engineers identified issues with the aircraft's highly swept, narrow-chord wings being unstable. Ralph Schick, a Vultee aerodynamicist, proposed a radical solution that led to the adoption of a delta wing configuration. This change dramatically improved stability and control, proving crucial for the aircraft at peak performance. Although delta wings had been explored during World War II, particularly in German designs, the implementation in the B-58 was distinctly an innovation of Convair, leveraging lessons from earlier projects. The delta wing was essential for its stability and ability to fit within the Mach cone, a 3-dimensional shockwave pattern generated at supersonic flight. By ensuring the wings stayed within this cone, airflow over them remained effectively subsonic, minimizing drag and enhancing speed. But the technological innovations didn't stop there. One of the most technical innovations of the model was the area rule, a concept that Convair had first experimented with on the F-102 Interceptor, rarely seen at the time. This design principle, conceived by NACA's Richard T. Whitcomb, shaped the fuselage to taper in where the wings attached, creating a Coke bottle effect that significantly reduced drag at transonic and supersonic speeds. The Hustler was also notable for its compact dimensions compared to contemporary bombers, measuring 95 feet in length and 57 feet in width. It could carry substantial ordnance, including a single 9-megaton B-53 nuclear bomb or up to 4 B-43 or B-61 nuclear bombs. To support such heavy payloads while maintaining high performance, Convair engineers developed an innovative structural design using a honeycomb sandwich construction. This involved layers of fiberglass honeycomb between aluminum panels, all bonded together with heat-resistant adhesives to form the aircraft's wings, ensuring a combination of high strength and low weight, essential for the aircraft's fuel capacity. Incorporating these advanced technologies instead of a bomb bay, the B-58 also featured a unique external pod system that allowed for flexibility in carrying additional fuel, weapons, and equipment. However, this modular approach posed design challenges as changes to the airframe often necessitated modifications to the pod's configuration, complicating the design and testing processes. One of the most unique aspects of the Convair B-58 Hustler was its crew configuration. The model's complex operations required a crew of 3, a pilot, navigator, and defense systems operator, each housed in their own separate cockpit in a tandem arrangement along the aircraft's fuselage. Because of the isolation, the crew had no physical contact. Communication among the crew members was facilitated through an intercom system, and for emergency communication, a string and pulley system and even sign language were sometimes used. For the more stressful moments of an operation, the Hustler had a special companion in the form of Sexy Sally, a female automated voice warning system that alerted the crew to various flight conditions and potential emergencies, as it was believed that a woman's voice would stand out against the cockpit noise and make it easier for the crew to notice and react. The B-58's dependence on speed for defense introduced substantial hazards for the 3-person crew, as conventional ejection at high velocities could be fatal. To address these dangers, the Hustler incorporated a sophisticated ejection system where each person had an ejection capsule that ensured safety within a clamshell enclosure. This advanced system, capable of ejecting at an altitude of 70,000 feet at up to Mach 2, came with an attached oxygen cylinder, enabling the pilot to control the aircraft up until ejection. Once deployed, the clamshell could serve as a life raft, providing critical survival support post-ejection. Despite its advanced technology, the Convair B-58 Hustler faced a significant challenge: its limited range. As a bomber designed during the Cold War to deliver nuclear payloads over long distances, having a substantial range without the need for refueling was crucial. However, the B-58's high-speed performance led to rapid fuel consumption, requiring frequent mid-air refueling for extended missions. This limitation increased the risk of exposure to enemy defenses and sparked debates within the Strategic Air Command about the bomber's operational efficacy. The type's entry into the SAC arsenal was nearly jeopardized as it faced potential cancellation multiple times during its development. Innovations in aerial refueling techniques did extend its operational reach, yet doubts remained about the practicality of an aircraft so reliant on refueling. Moreover, the B-58's development and testing phase was fraught with challenges, including the loss of 5 of the first 20 aircraft to issues ranging from structural stress to unexplained incidents. Such a high accident rate fueled concerns that the aircraft was rushed into production prematurely. Despite skepticism from some quarters, including SAC Commander Curtis LeMay, who favored a new design, the project received staunch support from Major General Albert Boyd, commander of the Air Research and Development Command. He advocated for the bomber's advanced capabilities in a progress report, stating, quote, "The B-58 is a major advance considering that we are attempting to more than double our speed capabilities. For that reason, I believe that it has a place in the Air Force inventory. Since we are attempting such a major advance, there is very naturally a high degree of risk." On October 15, 1959, the Convair Hustler proved naysayers and skeptics wrong when a model sustained speeds greater than Mach 2 for over an hour, covering 1,680 miles in only 80 minutes and with 1 refueling. Finally, the B-58 was officially integrated into the Air Force the following year. Should the Cold War turn hot, her role within the service was to cruise just below the speed of sound, accelerate beyond Mach 2 at altitudes exceeding 50,000 feet, and strike targets up to 500 miles away before returning to base. At the time the B-58 entered service, adversaries were still developing effective surface-to-air missile systems and high-altitude supersonic fighters. This allowed the Hustler to execute missions with minimal resistance and optimal efficiency. During the early 1960s, the B-58 fleet broke numerous speed and distance records in aviation, earning prestigious awards including the Harmon Trophy, the Mackay Trophy, the Thompson Trophy, the Bendix Trophy, and France's Blériot Cup, thanks in part to strategic aerial refueling. To enhance operational safety, Convair and the Air Force introduced the TB-58A, a dual-seat trainer variant that mirrored the flight characteristics of the operational models. The introduction of these trainers significantly reduced accidents among the operational B-58 fleet. Nonetheless, challenges when operating the aircraft persisted. The B-58 was one of the most challenging aircraft to operate in the entire United States Air Force arsenal. Its operations caused continual frustration for everyone involved, from designers to pilots, especially the defense systems operator who managed a complex array of systems within their own cockpit. The Hustler's delta wing configuration lacked horizontal elevators or wing-mounted ailerons. Instead, it utilized a sophisticated system of linkages connecting the wing's elevons, a combination of ailerons and elevators, to the large rudder. The B-58's fuel system was also intricate, requiring vigilant monitoring and adjustment. At Mach 2, the center of lift naturally shifted aft, necessitating a corresponding shift in the center of gravity, which was achieved by transferring fuel to balance tanks. Of the 116 B-58s constructed, 26 were lost, resulting in the deaths of 36 crew members. In June 1961, a B-58 that had previously completed the first supersonic transatlantic crossing from New York to Paris in record time crashed during a French air show. Another serious incident involved a Hustler, carrying 5 nuclear weapons. It slid off the runway at Bunker Hill Air Force Base and burst into flames. While the weapons themselves burned, radioactive contamination was detected in the area for years afterward. The high number of accidents and fatalities associated with the B-58 was likely due to its lightweight frame and rush development, making it more prone to structural failures. While the B-58 Hustler's main defense was its unparalleled abilities, this trait also contributed to its challenges. Despite its remarkable performance, the B-58 was deployed in only 2 operational units. However, once crew members mastered its flight characteristics, it became beloved and highly regarded among Strategic Air Command personnel. According to Navigator Bombardier Ben Badley, quote, "Crews wanted to get in it real bad. It was an airplane careers were made from. Not many people can say they went twice the speed of sound." By 1961, the B-58 Hustler's expenditures had escalated to a staggering $3 billion, around $30 billion in today's dollars. Operating the Hustler proved costlier than other bombers. It required $1,440 per flying hour for maintenance, in stark contrast to the B-52's $1,025 and the B-47's $361. Moreover, for every hour of flight, the B-58 demanded 35 hours of maintenance according to ground crews, underscoring its intensive upkeep demands. Despite initial enthusiasm from its operators, the escalating costs and extensive logistical demands began to fuel doubts about its long-term viability. But most importantly, the technological landscape was rapidly evolving. During the same decade that saw the Hustler's debut, advancements in surface-to-air missiles, high-altitude supersonic fighters, and intercontinental ballistic missiles signaled a shift in strategic military capabilities, ultimately marking the obsolescence of the B-58. By then, speed itself wasn't enough anymore. The final flight of a B-58 took place in January 1970, with the fleet being retired without ever being adapted for conventional bombing roles. Despite its checkered service record, the B-58 Hustler left a lasting impact on the field of supersonic aircraft development, holding records that remain unbroken to this day. Reflecting on the B-58, Ben Badley captured the sentiment perfectly. Quote, "Am I proud to be associated with this great aircraft? You bet your life. Would I do it again in a heartbeat? Was I ever scared? Always." The F7U Cutlass burst onto the aviation scene like a visitor from the future, straight into the 1950s. Its radical design, featuring a tailless silhouette and dramatically swept wings anchored to a short, robust fuselage, defied the conventions of the time, looking more like a starship than an aircraft. This Cutlass boasted an uncommon twin-engine configuration, a rarity for fighters during this period. It was powered by twin Westinghouse J-34 turbojets flanking the fuselage, which not only provided blistering thrust but also endowed the F7U with a spacecraft-like visage. The power plants were ingeniously integrated, with air intakes boldly positioned at the forward sides of the fuselage, sharpening its aggressive angular profile. Moreover, the F7U was a trailblazer in incorporating power-boosted hydraulic controls, a groundbreaking advancement that enabled crisper handling and nimble maneuverability at soaring speeds and dizzying altitudes. It also came equipped with an ejection seat, a vital safety mechanism in the high-stakes era of jet experimentation. However, when this sci-fi-like aircraft took to the skies, it turned into a nightmare. Its ambitious tailless design caused dismal stability and control issues. Underpowered and unreliable engines, combined with severe structural deficiencies, earned the aircraft a notorious reputation as a death trap. Fatal accidents increased, including one where the pilot ejected, leaving the jet to fly out of control around San Diego for half an hour. Whispers spread about the Cutlass's problematic Nazi DNA. The question loomed large. Had the seized German research, which laid the groundwork for the F7U, been the catalyst for its catastrophic failures? Could the Cutlass be redeemed? It was a warm autumn day in 1951 at Patuxent River Naval Air Station in Maryland, and Lieutenant Commander Edward Whitey Faitner was buzzing with anticipation. He got the call from an admiral at the Naval Air Training Command, offering him a coveted spot with the Navy's premier flight demonstration team, soon to be known as the Blue Angels. He remembers the moment. Quote, "It's a big deal to snag a Blue Angel slot. You're treated like royalty, crisscrossing the nation, rubbing elbows with folks from all walks, dazzling at air shows, pulling off some top-notch flying and drumming up support for Navy recruitment. There's hardly a gig that tops it." Faitner's burning question was simple. Quote, "What bird are we flying?" The admiral answered what the young pilot feared the most, the F7U Cutlass. As a seasoned test pilot with ample stick time in that very jet, Faitner's response was swift. He resigned right there and then. Spawned from the innovative swept-wing, tailless designs of Germany's Arado during World War II, the Chance Vought F7U Cutlass was a stark departure from the conventional. She boasted no tail, her sweeping wings sprawling 496 square feet, an impressive span. Her towering nose gear, a pioneering fully steerable system, elevated the pilot 14 feet off the deck. The Cutlass also featured a number of elements new to the U.S. Navy, including fully steerable landing gear, high-pressure hydraulic flight controls, and a new jet engine design. Vought designed the Cutlass for speed, to harness the power of jet technology to the limit, and for that reason they had decided to venture into the enigmatic technology research Germany had conducted by the final years of World War II. Based on the German conclusions, Vought decided to go with a tailless, swept-wing fighter, elements which the airplane's designers hoped would reduce drag at high speeds. Hopes were high for the twin-engine jet, with one 1948 article predicting that the F7U would prove not only to be the Navy's fastest airplane, but that it would eventually burst through the sound barrier as well. But by 1951, pilots like Faitner knew better. They had learned to fear the Cutlass and avoid it at all costs, even if it meant ruining their careers. The Chance Vought F7U Cutlass was a case study of an ambitious but flawed design. It suffered from chronic hydraulic leaks, erratic pressure dips, and underperforming engines. Troubles that, while not uncommon in early jets, were far more severe than those of its contemporaries, such as the reliable Lockheed P-80 Shooting Star, America's first mass-produced jet fighter, which had proved its mettle as a safe and competent combat aircraft. The Cutlass's radical design, inspired by wartime German research, became its Achilles' heel. The individual who had brought German knowledge to America was Waldemar Voigt. Voigt was a former senior designer for Messerschmitt AG, the German aircraft manufacturing company responsible for many of the Nazi fighter aircraft that terrorized the skies during World War II. In the 1940s, the German aircraft industry had built up an impressive technical background in swept-wing design aircraft. At Messerschmitt AG, Voigt oversaw several experimental aircraft projects for the Luftwaffe, the German aerial warfare branch. He also developed the Messerschmitt P-1110 and P-1112 projects, involving designs for a single-seat high-altitude interceptor and a fighter powered by turbojet technology. After the war ended, Voigt moved to America to work with Vought. He supervised the development of new aircraft inspired by his knowledge of German swept-wing designs, and by the time the Navy made an official requisition for a new swept-wing jet fighter, Vought was already working on the prototype of what would become the Cutlass. The aircraft's first flight took off on September 29, 1948, under the command of Vaught's chief test pilot J. Robert Baker, from Naval Air Station Patuxent River in Maryland, achieving speeds up to 625 miles per hour. Subsequent test flights soared beyond expectations. However, in their quest for ultimate speed, Vaught's engineers had relied too much on German research, inadvertently creating a nightmare for American pilots. Lieutenant Commander Edward Whitey Faitner's decision to resign from flying the Cutlass was well-founded. Having previously tested the jet in Carrier Division flight trials, he harbored a deep-seated dread for the aircraft. Quote, "Beyond the factory testers, 3 of whom had already perished in this jet, only one other soul had flown the Cutlass before me. He'd wrestled with severe control issues, managed to land without crashing, stormed in, hurled his helmet down, and declared, 'I quit.'" By the summer of 1951, Faitner had thoroughly tested the F7U, concluding it was unsuitable for the Blue Angels. Quote, "We realized straight away it wasn't the answer. Still, the Navy pushed for more trials. I even landed it on a carrier 14 times before the fuselage snapped in two right behind the cockpit on touchdown." The push to feature the aircraft was heavily politicized. Faitner recognized the pressure. Quote, "There were congressmen, senators, and a few high-ranking officers pushing for their pet project to be the face of the Blue Angels." Ultimately, the team opted for the more dependable Grumman F-9F Panthers, confining the troublesome F7U Cutlass to solo flights by Faitner and Lieutenant Mac McKnight, who were eventually persuaded to continue the tests. Faitner seemed to be stuck testing the now infamous jet, and his loathing for it would only grow. The Navy held onto the Cutlass with unwavering determination, convinced that relentless testing would smooth out its defects and mark a monumental advancement in the quest for the ultimate 20th century fighter. On paper, the Cutlass was an unmatched aerial beast, boasting a top speed of roughly 680 miles per hour and a maximum operational altitude of about 39,900 feet. It packed a blistering punch with its 420 mm cannons. It featured an avant-garde nose landing gear strut that elevated the pilot's seat 14 feet above the ground. It was equipped with ailerons for pitch and roll control, and a hydraulic system that delivered artificial feedback, allowing the pilot to sense the aerodynamic forces at play. Armed to the teeth, the Cutlass could haul 2 2,000-pound bombs on its inner pylons and 4 AAMN-2 Sparrow air-to-air missiles alongside its quartet of 20 mm cannons. When the Navy declared the winner of the request for proposals, the prototype's designation shifted from V-346 to the Vought F7U Cutlass. On paper, this aircraft was a true powerhouse. With such impressive specs, it was expected to honor its futuristic appearance by performing like a fighter out of this world. Once tests confirmed the F7U prototypes met all Navy standards, an order for 14 units was swiftly placed. Yet ironically, as full-scale production ramped up, so did the problems, pushing the Navy to demand more potent engines. Due to continual struggles with its power plant, the jet's second prototype was scrapped, After several adjustments, the third prototype emerged as the definitive model. Outfitted with Westinghouse J46W8B turbojets, the Navy rolled out 288 jets to 13 squadrons. Billed as supremely adaptable in tactical operations, the Cutlass's performance initially fell flat. Its turbojet engines lacked the thrust for effective carrier operations, leading to unsafe landings and takeoffs. Moreover, the jet was prone to engine flameouts in wet conditions, raising alarms among pilots and Navy brass. Fighter Squadron 81 was the first to be equipped with the Chance Vought Cutlass. Other squadrons, including Strike Fighter Squadrons 83, 116, 124, 151, and 212 also deployed with the jet, but most of the Cutlasses were ultimately grounded due to operational challenges. Accidents mounted rapidly. The Cutlass, infamously dubbed the Widowmaker, Ensign Eliminator, and Gutless Cutlass, quickly earned a notorious reputation. High-profile mishaps included the July 7, 1950 incident when Vought test pilot Paul Thayer ejected from a flaming prototype during an air show. Similarly, on July 26, 1954, Lieutenant Floyd Nugent watched helplessly as his rocket-loaded Cutlass circled San Diego's North Island for nearly half an hour before ditching near the shore after he ejected. Lieutenant Commander Paul Harwell's experience on May 30, 1955, added to the infamy when he bailed out just after takeoff as his left engine burst into flames, spending more time parachuting from Cutlasses than flying them. One of the most harrowing episodes unfolded on December 11, 1954, during a low-altitude, high-speed demonstration at USS Forrestal's christening in Newport News, Virginia. Lieutenant J.W. Hood's F7U disintegrated mid-flight due to a wing-locking malfunction, leading to his fatal crash into the water. This was followed by another disaster aboard the Hancock on July 14, 1955. Amid operations by Fighter Squadron 124, Lieutenant Commander J. Al Kyer's F7U Cutlass tragically failed to gain sufficient power during an approach, clipping the carrier's deck edge and erupting in flames, a disaster captured on camera, leaving an indelible image of chaos and destruction. This series of tragic incidents prompted the captain of USS Hancock to issue a stern command. All Cutlass aircraft were to be removed from his ship, a clear mandate to protect his crew from the troubled jet, despite the Navy's hesitation to officially retire these notorious death traps. Months after his abrupt resignation, Lieutenant Edward Whitey Faitner reluctantly agreed to join the Blue Angels, even if it meant piloting the notorious F7U Cutlass. During the 1953 season's inaugural show, Faitner, who had been closely involved with the F7U program, faced a critical failure. All hydraulic systems failed during a full afterburner takeoff and steep ascent. He struggled to gain enough altitude for a safe ejection, but fortunately the jet's backup system kicked in just in time. While executing the emergency landing, Faitner sliced through trees at the runway's edge, causing the left engine to ignite. Despite hydraulic fluid leaking profusely, he executed a sharp turn to align the plane with the runway, managing a spectacular, albeit fiery, landing that thrilled the onlookers. Despite these heroics, Faitner remained skeptical of the Cutlass, and the drama continued. In a notable incident, a Vought F7U Cutlass marked the first aircraft to touch down on the new runway at Chicago's O'Hare International Airport. En route to a show at Glenview Air Station, Lieutenant Hardin McKnight, piloting a Cutlass, suffered an engine flameout. Fortunately, Faitner was co-piloting and well-versed in handling the Cutlass's quirks. Directed to make an emergency landing at the newly expanded and renamed O'Hare Airport, they found the runway curiously covered in peach baskets meant to deter landings. Ignoring this makeshift barrier, Faitner and McKnight landed squarely on the baskets. Following these harrowing episodes, the Blue Angels finally judged the two Cutlass jets as unfit for demonstration purposes. The aircraft were eventually sent to the Naval Air Station in Tennessee, where they served as maintenance instructional airframes for the Naval Technical Training Center, marking the end of their turbulent service in the skies. Of all the designs that came out of the jet age, the Vought F7U Cutlass initially seemed poised to break the sound barrier with its futuristic swept-back wings and distinctive design. Despite its twin engines and advanced hydraulic system, the F7U fell short of expectations, lacking the necessary thrust and being too cumbersome to achieve supersonic speeds. At 30,000 feet, the Cutlass barely managed to reach Mach 0.98 and 0.99, even with afterburners engaged. Theoretically, it might have matched the speed of sound in a power dive, but in practical terms, this remained an unfulfilled aspiration. As the Cold War tensions escalated in the early 1950s, the demand for American aircraft to carry novel nuclear weaponry skyrocketed. New carrier-based attack planes became the forefront of this strategic shift. In 1957, Vought undertook a comprehensive analysis of all major incidents involving the Cutlass, documenting 78 accidents over 55,000 flight hours. Remarkably, about a quarter of all F7U models were lost to these mishaps, giving the Cutlass the dubious distinction of having the highest accident rate among all Navy swept-wing fighters. This dismal safety record largely stemmed from the application of cutting-edge design principles and aerodynamics that were not adequately supported by the era's available engine technology and relying on German wartime research that, while way ahead of its time, did not have the practical testing required to guarantee a safe and reliable system. The Cutlass had all the makings of an ideal Cold War fighter: sleek, innovative, and ostensibly capable. However, its subpar carrier operation performances and frequent accidents rendered the program untenable. The Vought F7U Cutlass was officially retired from service in March 1959, making way for its more effective successor, the F9 F8 Cougar, which served the Navy for nearly 2 decades. The Luftwaffe faced a critical problem. Building a strategic bomber capable of penetrating deep into the Soviet Union required engines with at least 2,000 horsepower, an unheard-of feat at the time. In a daring gamble, Heinkel Flugzeugwerke took a colossal risk. They fused 2 Daimler-Benz DB 601 engines, creating the monstrous Daimler-Benz DB 606 power system. With these twin powerhouses, they crafted the Heinkel He 177 Greif, effectively one of Germany's first 4-engine bombers. The result was revolutionary: a massive warbird capable of reaching 565 kilometers per hour, outrunning many contemporary bombers and boasting an exceptional range of up to 6,500 kilometers. Armed to the teeth with 7.92mm MG-81 machine guns and a 20mm MG-151 cannon, it provided robust defense against enemy fighters. It could carry up to 6,000 kilograms of bombs, including Germany's heaviest aerial ordnance and guided missiles like the Fritz X. This innovative engine configuration proved to be its Achilles' heel. The He 177's engines were prone to overheating and catching fire, leading to a series of catastrophic incidents. Crews soon nicknamed it the Flaming Coffin, One-Way Bomber, or Volcano. Even Hitler and Göring despised the warplane. Despite its flaws, the He 177 remained Germany's only long-range heavy bomber. Against all odds, brave pilots pushed the Flaming Coffin to its limits, determined to transform it into a weapon that could change the course of the war. Even during the 1930s, Germany knew it was gearing up for war, preparing for a bold, seemingly impossible task: conquering the Soviet Union. This monumental challenge required aviation technology far beyond the Luftwaffe's current capabilities. Specifically, a strategic bomber capable of striking deep into enemy territory and demolishing the Soviet Union's factories in the Ural Mountains. General Lieutenant Walter Wever, a daring and innovative strategist, was the mastermind behind this audacious plan. Wever believed the only way for Germany to unite Europe under the German flag and defeat the Soviet Union was through mastering strategic bombing, using long-range bombers to cripple a nation's war-making ability by destroying its factories and military assets. He plainly explained his strategy, quote, "to paralyze the enemy armed forces by stopping production in the armaments factories." Wever's views clashed with those of other German strategists like Ernst Udet and Hans Jaschonek, who favored smaller, cheaper aircraft for the Luftwaffe's future. Despite these conflicting opinions, Wever managed to launch the Ural Bomber program in 1936. On June 3rd of that same year, he released the first specifications for Bomber A, Germany's initial foray into strategic bombers. This design called for a significantly more advanced aircraft with higher speeds, longer range, and larger payloads. Fate, however, dealt a cruel hand. On the very day Bomber A was requested, disaster struck. Wever took off from Berlin, bound for Dresden to deliver a lecture at the Luftkriegsschule Klotzsche to eager Luftwaffe cadets. He planned to return to Berlin immediately after to attend the funeral of World War I hero Karl Litzmann. In his haste, Wever neglected proper pre-flight checks on his Heinkel He 70 Blitz, failing to remove the aileron gust locks. Just the day before, he had been warned about his lack of familiarity with the aircraft. The engines roared to life as the Heinkel sped down the runway. Moments after takeoff, the inevitable happened. The plane struggled and the left wing dipped sharply. Panic gripped Wever as he fought for control, but it was too late. The aircraft shuddered violently, stalling at a dangerously low altitude. In a split second, the Heinkel cartwheeled, smashing into the ground with a deafening crash. Wever's loss dealt a severe blow to the German strategic bomber program. The Luftwaffe shifted its focus to smaller, cheaper combat aircraft. However, Wever had managed to leave one requisition behind, enough to cement his place in history. The requisition left by General Lieutenant Wever seemed almost ludicrous to many German warplane manufacturers. To create a bomber capable of flying deep into Soviet territory, the Reichsluftfahrtministerium, or German Aviation Ministry, called for a warplane with 2 engines, each producing at least 2,000 horsepower. In stark contrast, the Heinkel He 111, a capable interwar bomber, had just been upgraded with 2 Jumo 211F engines, cutting-edge V12 powerhouses, each capable of producing just over 1,300 horsepower. The Bomber A would need to go much farther and venture into unprecedented territory. Heinkel Flugzeugwerke immediately began to look for creative solutions to this unique problem. While a 4-engine bomber would have been feasible with engines like the Daimler-Benz DB601, this layout would have increased propeller drag, hampering performance in dive bombing. Instead, using only 2 counter-rotating propellers on a heavy bomber offered significant advantages such as reduced drag, minimized dive instability, and improved maneuverability. For the He 177, lead engineer Siegfried Günther decided to use 2 complex Daimler-Benz DB606 power system setups. These engines had already been used experimentally on the record-breaking Heinkel He 119 reconnaissance aircraft prototypes, but they had never been mass-produced. Each DB606 consisted of a pair of DB601 liquid-cooled 12-cylinder inverted V inline engines mounted side-by-side in a nacelle driving 1 propeller. On the He 119, these engines were centrally located within the fuselage, just behind its heavily glazed cockpit enclosure. The outer sides of each engine's crankcase were connected to the nacelle firewall through forged mountings, similar to those used for single DB601 or DB605 engine installations. Combined with the central space frame mount designed for the power system format, this setup resulted in a Daimler-Benz coupled twin crankcase power system, with 3 engine mount structures within its nacelle. 2 of these DB606S initially developed 2,564 horsepower for takeoff and weighed around 1,515 kilograms, 3,340 pounds apiece. Günther's He 177 aircraft design was ambitious, aiming to transform aerial combat capabilities. Initially, it featured an advanced evaporative cooling system for the engines, using pressurized coolant to handle higher temperatures. Although successful in prototypes, this system failed under the intense heat of the DB601 engines, leading to a shift towards traditional heavier radiators that increased weight and drag. Günther planned sleek, remotely controlled gun turrets for armaments to minimize drag and enhance crew protection, inspired by developments in the Junkers Ju 288. However, technical and production challenges necessitated a return to manned gun positions, notably a rear dorsal turret with a 13mm MG-131 machine gun, adding structural weight. Later models incorporated some remote systems, but the primary armament was a mix of manned and automated. Defensively, the HE-177 was equipped to handle attacks from various angles. A 7.92mm MG-81 machine gun defended the front, while the tail gun position, initially designed for a prone gunner, was later revised for an upright stance, improving comfort on long missions. The aircraft was heavily armed with multiple machine guns and cannons, including a 20mm MG-151, strategically positioned for optimal coverage. The aircraft also featured extensive Fowler-type flaps for better handling during takeoff and landing. Still, the wings struggled under stress, demanding costly modifications to enhance strength and safety, which further increased the aircraft's weight and compromised its combat performance. Despite deviating from its original revolutionary design, the HE-177 was a remarkable example of German engineering. It boasted a streamlined fuselage, a high-mounted straight wing with a wingspan of about 31.44 meters, and an elongated nose with a slim tail section. Designed for strategic bombing, its robust structure supported a significant bomb load and integrated fuel tanks for long-range missions. The HE-177 was a large bomber with a typical crew of 6, including a pilot, co-pilot, navigator, bombardier, dorsal gunner, and additional crew for defensive operations and flight engineering. Despite its modifications from the original visionary design, trials were not favorable for the HE-177 and its strategic bomber aspirations. The ambitious bomber proved to be atrociously inaccurate when it came to horizontal-level bombing. To make matters worse, without the constant support of Weber for the Ural Bomber Initiative, the Luftwaffe brass soon lost interest in the HE-177's role as a strategic bomber. Dive bombing, on the other hand, particularly with Stuka aircraft, gained favor for its pinpoint accuracy, proving highly effective in targeting small, critical infrastructures, such as bridges and ships. Technical evaluations revealed that Stuka bombing surpassed the accuracy of other bombers like the Dornier De-17S and Heinkel HE-111S. Ernst Udet, a prominent figure in the Luftwaffe, ardently advocated for dive bombing, influenced by the Condor Legion's successful applications in Spain. The strategy evolved to include glide bombing, a technique that, while not as steep as dive bombing, significantly improved the precision of attacks on larger targets like factories, potentially allowing a single aircraft to achieve what previously required many. Under this philosophy, and after its disappointing trials as a horizontal bomber, the HE-177 was selected to shift to a dive bombing role. To achieve this, the bomber had to undergo several modifications, increasing its structural strength to withstand the demands of glide and dive bombing. However, these changes led to a continuous increase in weight, which in turn created unresolved stress issues on the airframes. However, the most problematic issue with the HE-177 stemmed from the same powerful engines that had allowed its design. The twin crankcase DB606 engines, each a monstrous 1.5 metric tons, had a notorious reputation after a series of fiery mishaps that had already claimed several prototypes. It appeared that the HE-177A's cramped engine nacelles turned these engines into ticking time bombs. One of the primary culprits was the central exhaust manifold serving 12 cylinders, a design that caused the buildup of oil and grease to ignite routinely. When throttled back, the mechanical fuel injection pumps lagged, over-delivering fuel that leaked from faulty connections. The result was an engine prone to overheating and catching fire mid-flight. Oberst Edgar Peterson, the head of the Luftwaffe's test facilities, was acutely aware of these problems. Reports of the compromised DB606 design, the lack of proper maintenance access, and the absence of firewalls reached the highest echelons of command. By August 1942, Reichsmarschall Hermann Göring's patience had worn thin. His fury was palpable in his scathing remarks. Quote, Why has this silly engine suddenly turned up which is so idiotically welded together? They told me then that there would be two engines connected behind each other, and suddenly this misbegotten monster of welded-together engines one cannot get at appears. For the crew aboard each test flight, the reality was grim. The engine's poor ventilation and the extreme rearwards placement in their nacelles made routine maintenance almost impossible. At high altitudes, the oil foamed due to a flawed pump design, leading to inadequate lubrication and catastrophic engine failures. The subsequent fires turned the aircraft into a blazing inferno in the sky, leading crews to name the aircraft the Flaming Coffin, One-Way Bomber, or Volcano. The test program's progression only highlighted the severity of these issues. Engine fires became a terrifyingly common occurrence, with the DB-606 power plants often ablaze before the pilots could react. These incidents and the engine's mechanical coupling flaws rendered the He 177A0 series an aerial death trap. By September 1942, a desperate solution was sought. The HE 177A3/R2 was introduced, featuring redesigned nacelles and the new DB-610 engines. These modifications, including improved oil flow, better cooling, and exhaust system overhauls, finally quelled the fire hazards. Operational tactics also evolved to better utilize the HE 177's strengths. Initially deployed as a high-altitude bomber, the aircraft struggled due to its reliability issues. However, when used in lower-altitude roles, such as maritime strike missions and anti-shipping operations, the HE 177 proved its worth. It could carry heavy loads, including Fritz X guided bombs and H-293 anti-ship missiles, which were instrumental in targeting Allied shipping. The aircraft's range and payload capacity made it a valuable asset in these roles. One notable operation involving the He 177 was Unternehmen Steinbock, Operation Steinbock, also known as the Baby Blitz, a series of night raids against southern England from January to May 1944. Despite the improved reliability of the A5, the HE 177's performance during these raids was mixed. The aircraft could deliver heavy bomb loads over long distances, but its vulnerability to Allied night fighters and persistent mechanical issues limited its overall impact. The HE 177's operational history also included a lesser-known role in anti-submarine warfare. Equipped with depth charges and bombs, the aircraft patrolled the Atlantic and Bay of Biscay, aiming to disrupt Allied submarine operations. However, this role was secondary to its primary strategic and maritime bomber mission. By late 1944, the HE 177 had evolved into a reliable, albeit not widely used bomber. Despite its troubled beginnings, the aircraft's improved reliability, enhanced operational roles, and significant payload capacity allowed it to contribute effectively to the Luftwaffe's strategic and tactical operations in the latter stages of World War II. Weber's legacy endured, despite never achieving the ultimate goal of giving Germany a strategic bomber advantage in the war.